Hello, and today we'll talk about chapter 1.1. This is the first part, and today we'll talk about the definition of linear dependence. So let's consider a set of vector, let's say from V1 to all the way to Vp. We know that we can write this system as a homogeneous systems of equations when our vector v form linear combination with some kind of weights from x1 to xp, and this linear combination is equal 0. So then we can go ahead and solve this system, and if solution exists, there's two possibilities for this solution. First solution can be a trivial, which means that all weights from x1 to xp will be equal 0. And in this case, we define this situation as the linear dependence of our vectors from v1 to vp set. Another possibility would be that our solution is actually non-trivial, which means that not all our weights x will be a 0, or at least one of them should be non-zero. In this case, we say that our vectors are linear dependent set of vectors. And this is a very, very important concept in linear algebra, and it's essential for a lot of, for example, machine learning algorithms. You sometimes see people stuck for months trying to make algorithm works, and it takes a while to figure it out that the set is just like linear independence. So linear dependence is often required for a lot of computer algorithms. So dependence is so important that we are even given name to this linear combination equals 0. We call it the linear dependence relation. And the precise values for our weights x will actually tell us a lot about this system. So how do we find if our system is actually linear dependent or independent? Again, we just can go ahead and solve the system by reducing it to echelon form. And then we explore our solutions. Is it trivial or it's not trivial? And if we can find a non-trivial solution, for example, or if our system is linear dependent, we actually can write down explicitly our linear dependence relation. Okay, but it's probably too much information. Let's just try to go through example. Okay, let's take a set of three-dimensional vectors, v1, v2, and v3. And we will try first, try to figure out if this system of these three vectors is actually linearly independent. And if we find some kind of linear dependence, that we will try write down explicitly the linear dependence relation. Okay, and as usually, our first step is writing an augmented matrix of the system when we just put our vectors v1, v2, and v3 right next to each other. And then, of course, we will add the right-hand side, which is just a column of zeros. And again, as usual, we will try to reduce it to the echelon form. So we take our first row, multiplied by 2, subtract from the second. Then we take again our first row, multiplied by 3, subtract from the third column. And this gives us like very, very, very nice zeros here in the first column, and we'll make it a pivot column. Excellent. So now we have our second column, which is we need to convert our -3 in the pivot element by divided by -3. And we also need to make the second element of the first row a 0 to, again, to reduce it to the echelon form. So we can write down our echelon matrix. And again, the good news is that, again, we are missing the third pivoting columns, which is always a good news, which means that we have free variable, and this variable is x3. And the better even news is that when we have a free variables, we guarantee non-trivial solution. And looking at our definition, let's just go ahead and see what does non-trivial solution means. Okay, when we have non-trivial solutions, our system is actually linear dependent. Okay, let's go back to our problem. What do we try to figure out in part A? Part A asks us if the set is linearly independent. And the answer will be no, it's not. It's clearly linear dependent because solution is non-trivial. Okay, let's go to the part 2 then. Let's try to find the explicit linear dependence relation. So basically we need to find our weights x and write down our linear combination of weights on the vectors v. Okay, so when we try to find the solution, of course, we start from the bottom up, and we always check this last row, even though it's zeros. We need to make sure that it's a valid solution exists. Then we go ahead and write the second row, which give us a variable x2 in terms of our free variable x3. And then we repeat for the first row, which again give us the variable x1 in terms of free variable x3. So let's try to write down our vector s, which is the vector of x, in terms of our variables. Again, we have x2, x1, x2, and x3, and we will try to write it down in terms of our free variable x3. And it's form a really nice vectors. So now we have our vectors v's, we have explicit our vector x, and again we keep in mind that our x3, it's just a number, any number, absolutely any number. So we just plug it into this equation and form linear dependence relations. And it's, even though we know that x3 is any number, I find this equation is quite confusing. All the subscripts and numbers, it doesn't really help. Even though it's a linear dependence relationship, sometimes it's worth just, find one example for the variable x3 and just kind of try to look at the solution. For example, let's choose x3 is equal to 5. X3 can be any number. Why not 5? Okay, so in this case, what would be our vector x? And again, we multiply our x3 by 2, which give us the entry equal 2. We multiply x3 at the -1, give us -5, and the third entry is just x3, which is 5. And you probably noticed that this vector looks much friendlier than that one. So maybe we'll just write it down, one specific example of linear dependence relationship. Again, keep in mind that our x3 can be 1 or 500 or any kind of number, but it's worth to write it down. For example, you can see how this equation is look much cleaner and neater than that one. So I find it's useful to use the number as an example here. So, okay, we find a linear dependence relations. So now every time we have a different set of we have a different x3, we can write and down this linear dependence relations. Okay, now go ahead, go back to chapter 1.8 and try to work several more examples of the chapter.